This is section 9.3, graphing rational expressions. I'm going to go as quick as I can through this because we got a lot to cover, so if I move too fast, just hit pause and write stuff down and just take another look at it if you need to. Alright, first thing we need to talk about is why we can't divide by zero. That is the main concept of this whole topic. And you may have been told you can't do it in the past, but I want to explain why. So let's just consider a function, y equals 1 over x. All right, something where we would end up having to divide by 0 somewhere. Because if I put in 0, then of course I would be dividing by 0. So let's just do an old-fashioned XY chart. Plug in 1 for x, see what you get. Well, if I put in 1 for x, 1 divided by 1 is 1. Simple enough. All right, let's try something that's getting closer to 0. Let's try 0.1. Well, if I put it in a calculator, you'll see you get 10. And then let's try something getting even closer to 0, 0.01. Well, you'll see you get 100 when you do that. And we can keep making up things that are really close to 0. If I had that many millimeters, that'd be pretty close to 0. Or if I had 0.0001 anything, it'd be pretty close to 0. That's going to end up being 10,000. Let's put some more zeros in here. If I divide 1 by this number put in for x, well, that's going to have 7 zeros. So 10 million. Hopefully you're starting to see a pattern. We can't really divide by 0. We never can get there. But if we were able to divide by 0, we would eventually be at infinity. And that's the reason why you can't divide by 0. If you try to divide by 0, the answer is infinity. All right. So now let's consider what happens with a function we might be dealing with. Let's say you have y equals x plus 3 over x plus 2. Okay. Same deal. Let's do an old-fashioned chart. Let's plug in 0 for x, see what we get. Well, that's going to be 3 over 2. No problem there. Let's try plugging in negative 1. All right, that'll be 2 over 1, which is 2. No problem there. That works out. We could graph that. Let's plug in negative 2. All right, well, negative 2 plus 3 is 1. Negative 2 plus 2 is 0. Now we've got a problem. We can't divide by 0. So for right now, I'm just going to say problem. That's where we're going to keep going with this. Again, the main idea is you can't divide by 0, but what we're going to do is figure out what happens when you get to a point where you are dividing by 0. That's where all the key things that happen in this section are about. All right, another preliminary thing, continuous functions versus discontinuous functions. I put this in parentheses. Continuous functions are everything you've done probably your entire life up until today. Things like y equals 2x, that's a straight line. Y equals x squared, that's a parabola. By the way, these are all things you should know for the SOL. Anytime you have y equals x cubed, that's going to make some kind of shape like this. That's a cubic function. Okay? We say these are continuous because I can draw them without picking up my pencil. That's an easier way to remember that. If I can draw the whole thing without picking up my pen, you got it, it's continuous. Discontinuous, same logic. If I can't draw it without picking up my pen, then it's discontinuous. So here's the things you're going to encounter today. Instead of trying to come up with definitions, I'm just going to show you what you're going to encounter and then tell you about it and let you see what it looks like. And if we need to define things later, we can. But the first thing you're going to see is an asymptote. And what that is, it's a dotted line that I approach but never touch. You'll have vertical asymptotes and you'll have horizontal asymptotes. Sometimes you'll have both, sometimes you'll have one or the other. But again, an asymptote is a line you approach but never touch. So let's draw in what a graph might look like. Maybe something like this. That's a common rational function right there. That's a good example. All right. Another way to think about asymptotes. This has been the example I've used over the years that seems to really work. So imagine that you are looking at, just pick a wall near you. Look at that wall. All right. Imagine you stand up and I tell you to walk halfway toward that wall. All right. you go halfway. And I tell you to walk halfway again. All right, so you do that. And I just continuously tell you to go halfway toward that wall. Well, the question is, do you ever get there? All right. Well, off the top of your head, you probably say, duh, of course I do eventually get to that wall. But if you keep walking halfway towards something, once you get super, super close and you're only going halfway of that distance, you never actually do get there. And that's probably the best way to think about an asymptote. All right. A hole can be in any kind of graph, but you're missing a point. Somewhere along the way, you're missing a point that you just can't graph. I look like I'm crazy over here talking to myself. All right, two things to be aware of here. We got holes and asymptotes. All right, so that's two things I just went over on the graph. The way you find these, you want to take whatever equation you have. What I would do is just pause it right now, write these down, but take whatever equation you have, set the denominator equal to 0, and you can do one of two things. Actually, you do both of these. You'll have either one of these situations or both happen. First thing is if a common factor divides out, and you'll see that in an example coming up, you have a hole in the graph. If nothing divides out, you have a vertical asymptote. All right, I haven't told you how to do a horizontal asymptote yet. That's a different rule. All right, the way that's going to work is there's two options for this. You can do either one. And again, you'll see this in an example soon. But when you get a function, plug in a huge number for x and just see what happens. All right? Or think about the end behavior. Graph it and think about the end behavior, the way we've been defining it all year. All right. I know that was clear as mud, so let me actually go through and show you a couple examples here. All right. First thing, horizontal asymptote. So the two ways I said to find that is to plug in something huge for x. So imagine we plug in 1,000,000 for x, okay? So be 1,000,000 over 1,000,000 minus 2. And hopefully what you're starting to think right now is, well, that minus 2 really doesn't make much of a difference, and you're right. Because in the grand scheme of things, the bigger the number I plug in, this is going to be really, really close to 1. I'm going to use that approximate sign. It's really close to 1. So horizontal asymptote is y equals 1. Horizontal line at 1. Okay. Vertical asymptote. All right. Think back to the other two rules you should have written down now. Take the denominator and set it equal to 0. All right. This will help us find a hole or an asymptote. All right. Well, get x equals 2. So that's either a hole or an asymptote. The difference is whether something divides out. And there's no common factor here that's going to divide out. So this is a asymptote. And in this case, there is no hole in the graph. Okay. So vertical asymptote at y equals 1, vertical asymptote at x equals 2, no hole in the graph. All right. Now, I don't expect this to make a whole lot of sense yet. It's okay. You might want to check out the problem again after we graph it, but let's go through and do the graph. Hopefully y'all can see this okay. Let's do x divided by x minus 2. All right, we'll take a look at the graph. And now the things we've been doing should start to make more sense. At y equals 1, we have a horizontal line that we approach but never touch. And at x equals 2, we have a vertical line we approach but never touch. Now let me talk to you about translating this to your graph. All right, you knew that at y equals 1, you had a horizontal line. So put that on there. You knew at x equals 2, you had a vertical line. Let's put that on there. Now your calculator is going to put a solid line in here. I want you to think back to what you know about math in general. If we have a vertical line, it's not a function. That's why we have vertical line test. So the vertical line shouldn't be a part of your graph. It's not a function if we really have a vertical line in there. That's an asymptote. It should be dotted. For whatever reason, the calculator doesn't do it that way. All right, there is no hole in this graph. So when we encounter one of those, I'll show you what it looks like. But just trace this graph along your asymptotes, and that's all I'm looking for. So it's something like this. Where you'll lose points on a test is if you actually cross the asymptote. Another way to think about it is like one of those invisible fences for a dog. Dog can't see it, but if he crosses a line, he'll know what happened. So it's an invisible line. It's dotted, but it has a real consequence. You can't cross it. So that's maybe a good way to think about it. Let's do a couple more examples, and hopefully they'll start to make more sense now. So, f of x equals x squared minus 9 over x plus 3. Okay. So same three things. We want to try to find horizontal asymptote if there is one, vertical asymptote if there is one, and we want to find a hole in the graph if there is one. And we're going to actually draw the graph. So these are the things you'll have to do on your homework. Let me just get a couple lines in here and get ready to go. Okay, think back through the process. To find a horizontal asymptote, we either plug in a ginormous number for x, or we just look at end behavior. Okay. Now I did a huge number for x last time, so I'll try to focus on end behavior this time. But I'm still going to plug in a huge number for x because I like doing it that way. Well, imagine if you had 1,000,000 squared minus 9. You can calculate that if you want to. Over 1,000,000 plus 3. And just think about this. Which one's going to win out? Well, 1,000,000 squared is a whole lot bigger than 1,000,000 plus 3. The minus 9 really doesn't make much difference. And honestly, the plus 3 doesn't make much difference because these are the big players. 1,000,000 squared divided by 1,000,000. But the top will always be 1,000,000 times bigger, or whatever number you choose to plug in will be that many times bigger. So this thing, what I have right now, if you did it on a calculator, would basically be 1,000,000 over 1. So the bigger, let me slide over so you can see it, the bigger x we plug in, the bigger answer you're going to get. So this would be a case where there is no asymptote. Okay. Now if you want to, it's always a good idea to graph stuff. Let me go ahead and start with a graph this time. And hopefully you'll see why there is no asymptote. Okay. So x plus 3. And this one makes a line. That's why there's no asymptote, because this one's going to be a straight line. Okay. So end behavior might not be a good way to talk about this one either. Sometimes end behavior doesn't work. That's why I like to go with plugging in a huge number here for x. All right, so horizontal asymptote, there was none. We'll go ahead and say none there. Okay. All right, vertical asymptote. Well, go back and look up the rule if you need to. You take your denominator, you set that equal to 0. So x equals negative 3. Okay. Now, if you look back to your notes, there was two possibilities. Either that cancels out or it doesn't. If it cancels out, if we can cross this x plus 3 out, we've got a hole in the graph. If we can't cross it out, then this is an asymptote. So what we need to do is actually factor. Factoring keeps coming up. It will keep coming up all year, I promise. If I factor that numerator, difference of squares, and x plus 3 was on the bottom, that's a common factor that divides out. So this is a hole. At x equals negative 3, we have a hole in the graph. We don't have a vertical asymptote. That's either a hole or an asymptote. If I find out it's a hole, it can't be an asymptote. Just like if I found out it was an asymptote, it couldn't be a hole. It's one or the other. Now, what's left is x minus 3. So in other words, y equals x minus 3. Well, that's my graph. Y equals x minus 3. Intercept at negative 3. Up 1 over 1, up 1 over 1. And where we have a hole is where x equals negative 3. So if I kept going back this way a little bit, what will happen is I have a missing spot down here. Where x is negative 3, that's right here. If I come down vertically, when I try to plug in negative 3, it won't work. I get a hole in the graph. I get an empty space. Now, I'm kind of pushing the limits of my paper, but we do continue on this line past there. Okay, so that's what it looks like. Now, the unfortunate thing, I've been telling y'all, calculator is not super useful in Algebra 2, and here's another case where it fails you. You look at this graph, and it looks like a solid line. The only way really to tell is to either try to do second trace value and put in -3. Nothing matches up with it. Or if we do second and graph, look at our table. Well, when you get to -3, you're going to see a problem. You're going to see an error message. But again, it's not going to show up on your graph. You're going to have to do the algebra to find this hole. So if y'all just copy what's on the calculator blindly, you're going to completely miss that problem on a quiz or a test. I'm looking for your algebra. Again, the calculator is not always the most useful thing to do. All right, last example. I know I told you I'd keep it short and it's still taking a while, but we're almost done. All right, same things. Horizontal asymptote, vertical asymptote, again, if these exist, they may not, a hole, and eventually a graph. Okay. All right, so horizontal asymptote. I'll do end behavior and I'll do the plugging in a huge number method. Again, I prefer this huge number thing. It seems to make more sense to me, but we'll keep working at it and you decide what you like better. All right, put 1,000,000 in. It doesn't have to be 1,000,000. You could plug in 1,000. You could plug in 100 billion. You have a calculator. I don't care what you do, but plug in something big, bigger than 10 definitely. Million squared down here, -2. Now, I'm not going to get a calculator out, but at least not yet. That's 2,000,000, and that is whatever 1 with 12 zeros minus 2 is, so something pretty close to this. I just noticed 12 zeros because I'm squaring it. So you can put the -2 on the end, but that -2 is really not going to do much. I mean, imagine taking the budget of the United States and taking $2 out of it. It really wouldn't make much difference. And really 2,000,000 compared to that, that's hardly nothing. So what you get down to is you're taking a really small thing divided by something huge. This is going to be about 0. You can divide these numbers out, and what you're going to get is something like this. There'll be some numbers back here, but you'll have 0 point a bunch of zeros. It's about 0. That's what that comes out to be. We can graph it so you can see how the end behavior is going to go. And again, I think it's a good idea to graph right away just so you know what you're going to end up with. There's no shame in graphing something right away. So here's what it looks like. It looks kind of scary. We can zoom in if we need to. I'm not going to do it right away. But I just want to think about end behavior. What happens if we go to infinity for x? Well, y is approaching 0. If we go to negative infinity for x, y isn't going, I guess what I need to clarify here, y isn't going up forever or down forever, it's approaching 0. So another way to think about this, our horizontal asymptote is at 0, either way we go. So horizontal asymptote, it's y equals 0. It's horizontal, so it's got to be y equals. That's another place you can mess up. Make sure you put y equals in there. All right, vertical asymptote. Again, the way to do that, take your denominator, set it equal to 0, see what you come up with. X squared equals 2, so x is going to equal plus or minus, take square root of both sides, square root of 2. Okay, and I'm expecting I'll be pretty quick at that by now. So that's where either a vertical asymptote or a hole is going to happen, plus or minus 2. So again, the catch is whether a common factor is able to divide out. In this case, 2x is on the top. There's nothing to factor. I don't have a 2x on the bottom anywhere. Nothing's dividing out. These are asymptotes. Okay. So 2 of them. X equals square root of 2. X equals negative square root of 2. And this will be another case where the calculator won't be real helpful in helping you find these. Pretty much have to do the algebra. It's the only way you're going to be able to find them. Hole, none. And that's just because neither one of these divided out as a common factor, so no hole in the graph. All right. And the way the graph's going to look, again, let's go with the algebra we figured out here. That's going to be a lot better than trying to mimic what's on that screen, because it's kind of hard to read. We have a horizontal asymptote at 0. I'm going to try to do this in a different color. It is the x-axis. Okay, and square root of 2 is about 1.5, so about halfway between 1 and 2, vertical line. Negative 2 is the other one, so about halfway between -1 and -2. Okay, so here's our boundaries. These are our invisible fences. Think of them that way. Okay, so again, look at the graph. On the left side, it's kind of doing this number. So just kind of goes like this. Again, main thing I'm looking for is that you don't cross your asymptotes. In the middle, it's kind of like a cubic function. Now, it does actually cross 0 here. When you have these middle parts, they can actually do that. It's kind of a weird design, but it's how it goes. And then, of course, the last part is this corner right here. All right, we're finally done.